This is the second presentation on global warming. This presentation focuses on past warm Earths, that many scientists believe that the best insight into the nature of a future warmer Earth comes from looking at past climate periods that were warm or warmer than now. This is a very important graph conceptually, not just for this presentation, but the whole issue of climate change. It's a typical XY graph, where time is on the x-axis and a climatic variable like temperature on the y-axis. The question is the change in temperature a cycle, something that goes up and down, random, like it was a hot week, or it was a hot month, or it was a cold month, or a wet week, or whether or not there's a trend over time. This presentation focuses only on real changes in climate that have taken place in the past. These three diagrams give you an idea about the magnitude of change in Earth's climate that I'll be talking about in this lecture. Let's first look at the lower left. There are four big periods of time that are highlighted in this graph. The mid-Cretaceous, when dinosaurs roamed the Earth, the early Eocene, the Pleistocene, and the last glacial maximum. The mid-Cretaceous was when it was much warmer and a lot more carbon dioxide, when dinosaurs roamed the Earth and there was a lot of biomass. The early Eocene is the last time the Arctic was ice-free. The Pleistocene is what some people believe to be a reasonable possible Earth for the year 2100. And notice that the amount of carbon dioxide is greatest in the Cretaceous, substantial in the Eocene, more than today in the Pleistocene, and that the last glacial maximum, the LGM, was very low carbon dioxide. In the upper left, you can kind of get at the idea of temperature of different past climates. The last glacial period in the past was much colder. Pre-industrial periods was colder than today. Today, the Pleistocene, kind of a middle-of-the-road perspective, and the Eocene and the mid-Cretaceous, much warmer. Yet another way of looking at it graphically is on the right. Carbon dioxide levels are on the y-axis. Notice that the amount today is pretty similar to the Pleistocene. It's nowhere as much as the early Eocene or the mid-Cretaceous. So you've got the CO2 levels bumping around in the last glacial maximum, quite low. The Industrial Revolution hits and it bumps up, and then you get three different models for how bad it's going to be in terms of our production of fossil fuels. This gives you an idea of what I'm going to be talking about in relationship to Earth and what we may do to it in the near future. You'll see this graph several times in this presentation, so take a good look at it. The x-axis is the change in temperature or radiative forcing. That 0 is the pre-industrial period. To the right are warmer Earths, to the left are colder Earths, and the y-axis is global temperature change. The principle of this is that as these different lines diverge from the pre-industrial period, the uncertainty or the confidence in the science decreases. The basic idea is that you see the plus or minus bar graphs, and they get to be very big in the Cretaceous. So the further away you get in time, the more the information I'm providing you is uncertain. The Cretaceous period was the last time when dinosaurs roamed the Earth. The mid-Cretaceous was really quite warm, but the end of the Cretaceous was also very warm. And look at the carbon dioxide levels. They are way high off the chart. So again, the certainty is low, but there's a lot of different evidence to indicate that it was a real intense greenhouse Earth with a lot of biomass, very wet, and could support giant life forms, dinosaurs. The Eocene came after the dinosaurs in the time of mammals, and it was around 35-40 million years ago, and the amount of carbon dioxide in the Eocene was very high. The amount of methane was very high, almost as high as the dinosaurs. And it wasn't until after the Eocene that you had icebergs begin to develop and develop Arctic sea ice. So the Eocene was really the last time the Earth was ice-free. One possible explanation for the extreme warmth of the Eocene was the release of a tremendous amount of methane from the ocean floor. And during this time of methane release and an ice-free Earth, there was a connection between Asia and North America, and there was a lot of life forms that crossed over this land bridge. So there's a lot of dispersal of different animal types that then led to diversification of new mammal families. In addition to methane release from the ocean floor, it's also possible that an intense volcanic period released a lot of carbon dioxide into the atmosphere, and the combination of CO2 from volcanism and the release of methane led to this intense warm period, where there was a lot of life and a lot of warmth. With increased interest in global warming, there has been an abundance of new models on past Earth conditions, and one of the models for the Eocene suggested it was ice-free, that the wetter places were wetter, that the dry locations were drier, and that there was a lot of seasonality. So it's a warmer, wetter future if we reach the Eocene conditions of super high levels of CO2 and methane. So if you look at the graph on the right, the time scale is reversed. The older period, 60 million years ago, is on the far right, and the present is on the left on the x-axis. So you're getting temperature or warmth for the y-axis as indicated by isotopes. So the Eocene was super warm, and then you get closer to today where the mid-Miocene was also warm, and then there's something called the Pliocene, where there was a piece of the Pliocene that was much warmer than today. The point of this slide is that the Miocene and the Pliocene Earths that were warmer than today, but cooler than the extreme Eocene or Cretaceous, had much higher sea levels. Before the Ice Ages, there was the Pliocene, and there's the thought that the Pliocene might be the best guess for what Earth might be like in 2100 with higher levels of greenhouse gases. Sea level was higher, the Earth was wetter, and the Earth was warmer, are some generalizations for information that we have. I return to this diagram because I want you to look at the lower left. There's last glacial maximum and average glacials. This was a time of Earth when carbon dioxide levels were lower than today, and it was much colder. So I'm going to explain what we know about the Pleistocene, or during the Ice Ages, about what Earth was like. The last 400,000 years during the Ice Ages, we have much better information about what Earth's climate was like. This record's incredible. It's 2 decades old, and it hasn't been improved upon. A lot of people drilled ice cores into Antarctica and Greenland, extracted the ice, and then got the air bubbles out of the ice and measured the methane, the carbon dioxide, and the deuterium that gives you the temperature of Earth. This is stunning. Look at it carefully. In the last 10,000 years, we were warm with more methane and more carbon dioxide. Not quite as warm as 140,000 years ago, and not as warm as 330,000 years ago. We've had violent swings in climate associated with swings in greenhouse gases. Another thing to take home is that during the entire Ice Age, CO2 was never above 300 ppm, or parts per million. This is stunning information that should tell you that if you want an ice age, drop carbon dioxide and drop methane levels way down, and you'll get a much colder Earth. You really should be glad you're not living in an ice age when it was much lower greenhouse gases, much colder. A lot of places were very dry. A lot of places were cold. A lot of places were covered in glaciers. So after the last glaciation, it was carbon dioxide that increased to help pull us out of an ice age Earth. CO2 is not an evil gas. It actually saved the planet many times in terms of bringing us out of ice ages. A very large scare is going on in the climate change research community. People are very concerned about the North Atlantic circulation of ocean water, where we know it as the Gulf Stream, but it really starts with the sinking of water around Greenland that then goes through the subsurface, reemerges out, and then becomes the Gulf Stream. It's a circulation system that transports warmth from the tropics towards the higher latitudes. It's a very important part of Earth's oceans and atmospheric circulation. So there's a chance that the ongoing changes in climate might reduce or shift this circulation system, reducing the Gulf Stream. And it's a thread that keeps popping up year after year over the past decade, that experts think the ocean currents are slowing. Experts find a mechanism that can collapse this ocean circulation system. The idea is that we can change things very fast in Earth's climate system, that if you mess with the circulation system, you can get a dramatic change in climate over a period of a few decades. This is one example of this thread of research where people looked at the data gathered from oceans and ocean cores in a very unique statistical way and published a paper saying there could be a collapse of the Atlantic meridional, that means changes in the ocean circulation system. And then I took a clip of a review of what other people think of this statistical research, saying that this could be decades away, and people were skeptical. So what I need to explain to you is that there is a broad spectrum. There's no consensus on whether the Gulf Stream and the Atlantic circulation system is stable or whether it's on the verge of collapse. And even if there was a consensus, I wouldn't trust a consensus, because I really think that scientists get into clubs and cliques. So it's hard to see sometimes where this club or clique is wrong. So just recognize that it's a possibility, but let's look at the past to see what happened to Earth the last time the circulation system collapsed. In the past, when the circulation system has collapsed, it's been because there's been an injection of a tremendous amount of fresh water in the area where the ocean waters sink around Greenland. That's happened in the past when you've had ice streams shoot a lot of icebergs out. The icebergs melt. That's a lot of fresh water on the surface, and it collapses the circulation system. So what happened in the past when the circulation system shut down? And it shut down many times in the last glacial period, in the last 100,000 years. There's a very funny movie, I think it's hysterical, called The Day After Tomorrow, where one of the premises of this Hollywood version of a movie is that the ocean circulation system collapses. There's a whole nother premise of it, but it's an idea to freeze New York City, have tornadoes in LA. It's a very funny movie, made in 2004. But my serious point here is that in the periods you see labeled H1, H2, H3 to H6, these are periods when we know that the circulation system collapsed. What happened is very different Earth. Within a few decades, the western U.S. got quite wet. In these periods, the West was wet. There were giant lakes in Utah and Nevada and California and Arizona. It was cold elsewhere. There were big shifts in climate. Some places got dry, some places got wet. The scary thing is that it can happen shortly. That when the Earth's circulation system collapses and climate changes, you can get all these changes within a few decades, and that's not very good when people want to live in a place for decades. But my larger point is the Earth isn't going to end. That what we know about the past is that there were changes and that there were winners and there were losers, even in this dramatic of a change. We know a lot more about the climate after the last glacial period because we have historic records and we have archaeological records of Egypt, of Rome, of the Maya civilization. The last 10,000 years, there were warm periods and there were cold periods, but it's been pretty stable, as typical for Earths that come out of a glacial period. You get a warm period that's pretty stable. The warmest periods were in the middle of the Holocene, when Rome rose, during the medieval warm period, and then it got a really nice cold snap, the Little Ice Age, and then it warmed up again. So there's a lot of changes that occur in the last 10,000 years. Lower magnitude, and again, there were winners and losers. This is the last time you'll see this diagram, and the point is that the last 10,000 years, or the pre-industrial Earth, is dead center. It's where we have a lot of confidence in the information, but the change, the radiative forcing, is much lower. So in the most recent past, we get the less dramatic changes in climate historically. This is an old paper, 2 decades old, but it hasn't been revised, and it's a classic. Let me see if I can explain what's going on. What these researchers wanted to find out is, in the last 10,000 years of relative climate stability, what was going on with the Asian monsoon in India, Southeast Asia, and in China. So to do this, they looked in caves, and they looked at other records to see what happened when the relationship of cold periods, warm periods, wetness, dryness in this region. And they concluded that it was the warm periods in the last 10,000 years, what's called the Holocene, were wetter in this region. So this is other research examining the same question about during the latter end of the Holocene, close to the present, what's the relationship between warm Earth and cold Earths and droughts? And lo and behold, they found that the Ming Dynasty ended, and a lot of other political era periods, the Strange Parallels drought, the East India drought, Basically, that there's a connection between political instability and drought and cold periods. That cold snaps brought droughts and political instability. And this kind of concerns me. There's some 3 billion people living in this part of the world, and we know that pre-industrial conditions have droughts when it's colder. Warmer periods in a pre-industrial Earth had much more reliable monsoon rains. So now you might be asking, okay, let's go back not just the Holocene, the last 10,000 years, but what's the connection over, say, 100 and 200,000 years of warmth and the Asian monsoon? And it's the same thing, that Asian monsoons tend to be stronger. You get better rains when there's warmer periods. And they know this from looking at sediment records in the oceans and isotope records in caves. It's a consistent signal. And here's the last of Dorn beating this drum to death. This is an old paper, some 20 years old, but it's another study using a different technique that in the last 10,000 years of relative Earth warmth, you had droughts in India during cooler time periods. I suppose my broader point here is that if I had my druthers worrying about 3 billion people on the planet depending upon the monsoon to not have famines that would be politically horrible, not to mention thousands and maybe more dying, you need warmth. If it gets too cold, you're going to have droughts. That's what the past tells us. I'm almost done. I have a very simple point to make, that in the last cycle, or the last couple cycles of very tiny climate changes, the Roman warmth, the Dark Ages cold, the medieval warm period, and the little ice ages. And then today, no matter what change you get, the impact is spatially variable. In the western USA, the medieval warm period had massive droughts. The Sierra Nevada much worse than today. But in other places, it was much better. So there's going to be winners and losers no matter the change. That's just the nature of how Earth's climate changes. In the warm, in the recent past, we tend to have droughts. But elsewhere, well, changes are different. So the idea is that every climatic change will have different winners and different losers. In summary, all past warm Earth possible analogs had wetter climates in general, but there were dry locations, and sometimes there are hints that the dry was drier. All past warm Earth analogs had robust ecosystems. The ecosystems didn't collapse. All past warm Earth analogs had very different locations of wet and dry. So every time you roll the die and you change the climate, there are different winners and losers generally. Lastly, Earth has long survived warmer climate conditions, but we simply don't know which or if past conditions will reflect, say, the year 2100 or 2200.